Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Acid-catalyzed ring expansion, cationic rearrangement of methylene cyclohexanes under thermodynamic control. Step 1. Identify the starting material. The reactant is cyclopentylidene with an isopropylidene unit. More precisely, it is 1-propan, 2-ylidene, cyclopentane, i.e., cyclopentane bearing an exocyclic is equal to CH3, 2 double bond. This is a cyclopentane ring with an exocyclic double bond to CH3, 2. Step 2. Protonation of the exocyclic double bond. Under H+ heat conditions, the exocyclic alkene is protonated according to Markovnikov's rule. Protonation at the terminal carbon of is equal to CH3, 2 gives a tertiary carbocation at the carbon bearing two methyl groups attached to the ring, i.e., a tertiary cyclopentyl carbocation at C1 of the ring, or protonation at C1 of the ring gives a tertiary carbocation on the is equal to Ce2 carbon. The more stable carbocation is the tertiary one on the exocyclic carbon plus CH3, 2 adjacent to the ring. Actually, both positions give tertiary carbocations, but the one that can ring expand is the cyclopentyl carbocation at C1. Step 3. Ring expansion via 1,2-alkyl shift. The tertiary carbocation at C1 of the cyclopentane ring undergoes a 1,2-carbon shift. Ring expansion. One of the C bonds of the cyclopentane ring migrates to give a cyclohexyl carbocation. This expands the 5-membered ring to a 6-membered ring, cyclohexane, placing the positive charge at an endocyclic carbon with a methyl substituent. Step 4. Deprotonation under thermodynamic control. Loss of a proton from the cyclohexyl carbocation gives the most stable, most substituted, Zaitsev, alkene. The endocyclic trisubstituted double bond in a methyl cyclohexane ring is more stable than an exocyclic methylene cyclohexane. This yields a trisubstituted endocyclic alkene, 1-methylcyclohex, 2-Na, or equivalently a cyclohexene with a methyl group corresponding to option D. Why other options fail? A is an aromatic conjugated product that would require additional dehydrogenation steps not possible under these mild conditions. B shows an exocyclic double bond on cyclohexane. This would be the kinetic product but not the thermodynamic one. Endocyclic alkenes are more stable. C shows a terminal exocyclic is equal to CH2 on methyl cyclohexane, less substituted, thermodynamically disfavored. D shows an endocyclic trisubstituted double bond in a methyl cyclohexane framework, most thermodynamically stable product, consistent with thermodynamic, heat, conditions. Therefore, the correct answer is D. Therefore, the correct answer is option D.